Good morning to all. So today we'll try to understand some more terms related to tensile testing of textiles. First we'll cover CSP. Okay, we know the full form of this word is count strength product. CSP is a value which we take only for Li of the yarn. We take the Li, find its breaking load in pound force, and then we measure the weight of that Li and find out the count in English count system, and then we multiply these two values. CSP is always taken in these units: Li breaking load in pound force and yarn count in NE. So it gives an idea of the yarn strength irrespective of yarn fineness. In the way we divide by linear density in case of tenacity, here we are multiplying by yarn count because it is an indirect system. It is a very popular test in industries because it is a rapid test, and both the things, count as well as strength, we can take from one single sample. So next is RKM. RKM is basically breaking length. We have already discussed breaking length. In kilometers, in a specific unit, kilometers. If we compare the numerical values, then we'll find that tenacity of yarn in gram force per tex is equal to breaking length in kilometers. It is called RKM. Maybe R is for rupture and KM is for kilometers. So this is rupture kilometer. Next, one more term we need to understand, that is fiber strength realization. What is fiber strength realization? It is the ratio of yarn tenacity and fiber tenacity. As we know that yarn tenacity is always lower than fiber tenacity if they are compared in same units. So if we find fiber strength realization, which is a measure of how effectively the fiber tenacity is being utilized in the yarn, it is never 100%. That means yarn tenacity is always lower than the fiber tenacity. In case of these cotton fibers, it is 30 to 60%, and these numbers are given 30 to 64% for short staple man-made fiber. For filament yarns, it will be higher, obviously. So fiber strength realization gives us an idea about the how one fiber contributes to the yarn strength. Fiber strength realization is more in case of finer and longer fibers. Next term we need to understand is fabric assistance. Fabric assistance. Okay, now this is a term related to fabric. Whenever we find the strength breaking load of a fabric and divide by the number of threads in that fabric strip, so that will give us strip strength per thread. And if we compare it with the single thread strength, we find that strip strength per thread is always greater than single thread strength. Why is it so? Now, if you are measuring the strip strength per thread warp wise, then weft is not directly contributing, but indirectly through the frictional contacts. Weft is also contributing to the strength. So we can understand that fabric assistance is a factor in which it is a binding effect of transverse threads on longitudinal threads, resulting in increased strength. Its value may be up to 1. It can be up to 1.8. Now the next term which we need to understand is time dependent tensile behavior. Up till now we have tried to understand the relation between load and elongation and stress and strain, these things. Now how the things changes when the time factor comes in the scene. So we'll try to understand two terms here, creep and stress relaxation. Creep is at constant stress, extension increases with time. It's very important topic. Listen carefully. At constant stress, extension increases with time. Meaning, if we take a fiber sample or any textile sample, fiber yarn or fabric, and we put some particular load to that sample, particular stress or load to that sample, then there will be some, we can see it from this graph that this is input, stress versus time. We have given some load for this much time, and after that we remove the load. Now how the sample behaves, strain, there is an instantaneous strain. This is instantaneous extension. If we put some load on any textile fiber, there will be instantaneous extension. After that, since we have this is instantaneous, now this is time dependent deformation, that with time, not with increase in load, with time extension is there. So this portion of the extension is called creep. Now if we remove the load at this point, if we remove the load, then there is instantaneous recovery also. Some amount of recovery is instantaneous. This is called creep recovery. Now creep recovery, we can divide it into two parts. This is primary creep and secondary creep, in which this is with time there is some recovery, and some particular this thing is permanent set. That means this part is not recovered. So this is time dependent recovery, this is instantaneous recovery, and this is permanent set. We can say here this is instantaneous extension and this is time dependent extension, which is called creep. Now the other term which is important is stress relaxation. This can be defined as at constant strain, stress reduces with time. Suppose we take a sample and we extend it to 2%, 4%, whatever, we give a constant extension for a long time. Now what happens? The stress developed inside the material decreases with time. That is, if you take a rubber band type polymeric material, fiber or anything, if you stretch it for a particular strain for some time and leave it for 1 day or 2 days, that rubber band will the tension inside that rubber band will reduce. You must have experienced it in daily life also. So stress reduces with time at constant strain. This is called stress relaxation. Okay. Now next term is elastic recovery. Elastic recovery is also time dependent property basically, and it depends upon the total extension. Suppose we have got a fiber or a yarn and you have extended it 2% and it has recovered 1.8%. So 1.8% is 1.8 divided by 2 into 100 will give you the recovery, elastic recovery, and other 0.2 part is plastic, that is permanent set. So elastic recovery is always quoted at a particular extension. You can always see in the tables that if we see the elastic recovery of different fibers, you will also always see that nylon recovery is itna percent at itna percent extension. We always quote elastic recovery at given percent extension. So it is elastic extension upon total extension into 100. Now one more term is used, work recovery, similar to elastic recovery. As we know now that the area under the curve is called work of rupture, area under the load extension curve. Now if this is a load extension curve of any fiber and this is the breaking point, without reaching at breaking point, at some point of extension, if we remove the load, so it will come back, and the comparison of area under the curves of these two lines, that is, this is total area under the curve and this is recovered area under the curve, that will give you the ratio. That ratio will be called work recovery. Work returned during recovery divided by total work done in extension. So now here this is extension line axis, so we can divide it into two parts. This is elastic extension because this part is already recovered, and this is plastic extension which is not recovered. So work recovery also we can report. There is one more term, mechanical conditioning. It is just a term we need to understand, that if we stretch a fiber far enough means after yield point, up till yield point, stress and strain are directly proportional, load and elongation are proportional. After yield point, there is a permanent set in the fiber elongation. There is a permanent set. That means fiber is elongated permanently. So that will change the load elongation curve of the already stretched fiber. So mechanical conditioning means stretching a fiber far enough to leave it with permanent set causes other changes in properties of fiber. Obviously, if a fiber is already stretched, then we'll use that fiber. Then its breaking extension will be reduced as compared to original fiber, and work of rupture will also reduce as breaking extension will reduce, work of rupture will also reduce. Okay, thank you. We'll continue in next class.